Okay, we are moving into probability part 2. If you are in class with us this week, then we will be working on this in class, working through some official prompts and moving forward with that. If you're not going to be in class with us, then this is something that you may want to work through pretty slowly. Make sure that you have all the details. Once you've seen the slideshow and you're ready to try the prompts, you can email me and let me know, and I will get those to you. Okay? So let's start out with random variables. We discussed some basic probability in the last probability slideshow, some very basic understanding of probability of two events, either happening at the same time, independent events, or the result of considering more than one outcome a success with our mutually exclusive events. So we're going to continue to expand on that. Let's kind of think about that in a perspective from random variables. So if you're not really sure what a random variable is, it's a number whose value depends on the outcome of a random process. So that might sound a little mathy. So let's look at some examples. Okay, if you flip a fair coin 3 times, X, the random variable, okay, flipping the coin is the random process. The number of heads we get, if we define that as X or any other variable, then X is the random variable that we're counting, okay? So again, that's a number whose value depends on the outcome of a random process. The number of heads I get depends on the outcome of the random process of flipping the coins, okay? If you roll a 6-sided die, okay, Y will be how much I have to win or how much I'm going to win. So that's based on, of course, this the result of the die roll. If I get a 6, I win $10. If not, I lose $1. So how much I'm going to win is a random variable. Again, a number whose value depends on the result of the random process of rolling the die. Okay, choosing a person at random from a population and recording his or her height. Z would be equal to the height, and it is the random variable. Okay, the random process is, of course, random selection of the person, and the value is the height that I am recording. Okay, so let's say we take a simple random sample of 25 people from a population. So I'm going to randomly select 25 and calculate the mean, okay, X bar. In this case, X bar is the random variable. And this is one of the most important examples that we're going to see in this, because probability distributions and distributions in general are a very, very solid foundational idea in statistics. Okay, so again, what is the random process? Choosing those 25 people randomly, and the value is going to depend on that selection, because based on who ends up in that selection will affect what the value of the mean is going to be there. Okay, so let's take that knowledge now and let's expand that a little further in something that we call a probability distribution. Okay, first of all, for any random variable, okay, we would like to know the chances for X in order to assume various values. Okay, so if we know how to do that, then we know how the distribution of those outcomes is going to look, okay, to us. So a probability distribution for a random variable is a listing of the possible values of whatever it is I'm recording, along with the probability of getting that particular value. Okay, so let's look at this example. If we flip a coin 3 times, our possible results can be these 8 outcomes that we've listed previously: heads, 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 tails, heads, tails, heads, tails, heads, 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 tails, 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 heads, tails, 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 heads, or tails, tails, tails. So these are all of the possible results. Okay, so my random process is the flip. My possible outcomes are here, okay? But that doesn't necessarily tell me the values of X until I have defined what X is going to represent, okay? If X is going to be my random variable, it's going to represent not an outcome, okay, but a specific count of something or measurement of something. In this case, it's the number of heads, okay? So Based on that, let's look at this table, okay? We're looking at each of the individual 8 outcomes here. And we're also making a list of if this outcome were to occur, what would the value of my random variable x be? Since we're counting heads here, tails, tails, tails would be a 0. Tails, tails, heads would be 1. Tails, heads, tails, 1. We could continue to go down the list and count the number of heads, which is what our focus is on in the random variable here. Okay, I can get anywhere from 0 up to 3 heads. Is each number of heads equally likely? Well, this should be something we're already able to say no, okay? Because if we look at all of these possible outcomes, there's only one way I can get 0. There's only one way I can get 3. But there are multiple outcomes that produce 2, and there are also multiple outcomes that can produce 1. Our basic understanding of probability at this point, we should be able to say confidently without going any further that when we do this, when we perform this coin flip, we're most likely to get 1 or 2 heads because those have the greatest number of possible outcomes which produce that result. Okay? We are least likely to get 0 heads or 3 heads because there is, again, only one outcome each that would produce that result. Okay, so far, this is something that should make sense to us if we take time to stop and think about it. All right, so now let's think about the distribution of x. Remember, so far here, we're just looking at the values x could be. How is that determined? It's based on the outcomes that are possible. If I know x is heads, then I have to look at the outcomes that are possible and think about the number of heads that could be in each one of those outcomes. If we move on to the distribution, what we're going to do at that point is we're going to look at how likely are each one of these individual outcomes. Okay? Now, here's what we've done. We're not specifically looking at the probability of the outcome as much as looking at the probability of the number of x, which is our random variable. So we're looking at the probability of getting 0 heads, of getting 1 head, 2 heads, or 3 heads in the flips that we have produced. Now, why 1/8, 3/8, 3/8, and 1/8? If you go back and you look at the outcomes, all of these individual outcomes are equally likely. That's because we know getting heads or tails is an equally likely result. Okay, 1/2 times 1/2 times 1/2. That's 1/8. 1 out of 8 outcomes here. Okay, can calculate it both ways. Regardless of whether it's tails or heads, that's true. Okay, now that's easy to see why 0 is 1/8. It's 1 out of 8 possible results that makes that happen. Same thing with heads. 1 out of 8 possible results that make that happen. So why are 1 and 2 3/8? Because 3 of these outcomes would produce 1. 3 ways I could successfully get 1 head in my results. And 3 of these outcomes produce 2. Okay, so we have 1/8 for 0, 3/8 for 1, 3/8 for 2, and 1/8 for 3. Okay, so the value of x, which is the number of heads, and the probability of that number of heads in my 3 coin flip is distributed in this fashion. Okay, so if we were to graph that, if we were to produce a graph of that distribution, here's kind of what we would see. And this is sort of a frequency measurement or a density measurement. We would see hopefully that 0 and 3 are the least likely outcomes, whereas 1 or 2 are equally likely. Okay. Now, if we're looking at a probability distribution, these are sort of the conditions that we have to be working under. All outcomes are mutually exclusive. And I want you to think about that. Getting 0 heads is mutually exclusive from getting 1. Okay. We can't do one series of 3 and get both 2 heads and no heads in that series at the exact same time. Okay. So they're mutually exclusive. All the probabilities assigned are between 0 and 1. Okay. It can't be more than certain, okay, or less than 0. The sum of the assigned probabilities must be 1. Okay. Now, why is that true? Why does the sum of the assigned probabilities have to equal 1? Because if we're going to flip those 3 coins, one of these things is certain to occur. We're either going to get no heads, 1 heads, 2 heads, or 3 heads. Those in the sum are the total of all of the possibilities that occur. Okay, so they have to add up to 1 because we're certain that one of these results must occur under the conditions that we've been given. Okay? So let's use the distribution to continue to think further about probability. Okay. After we know the distribution of the individual outcomes, then we can know how we can utilize that to think about the possible combinations of outcomes, more than just the probability of getting a specific number. Okay. For example, let's look at this probability. If you're not really familiar yet with learning to read these, I suggest that you practice. This is the probability that x is less than or equal to 2. Now, put that in context of the situation. Okay, now what does that mean? X, remember, represented the number of heads in a 3-coin flip. Okay, so we're looking for the probability that the number of heads in a 3-coin flip is less than or equal to 2. Well, which results then would meet these conditions? Okay, less than or equal to 2 would include 2. It would also include 1, and it would include 0. So that's why you see these probabilities added together, because any of these 3 outcomes now satisfy the success that I'm looking for in this individual example. Okay, I will accept 0 or 1 or 2. Okay, mutually exclusive events, so we can add those probabilities together. I'm increasing my probability of success because I'm willing to accept 0 or 1 or 2. Okay, so 1/8 plus 3/8 plus 3/8. So 7/8 of a probability that I would get 2 or less heads in a 3-coin flip. Okay, so that should make sense then, that the only probability left for 3 heads, because that's the only outcome that does not fit into here, is the complement of 7/8. It's 1/8. Because we know that we're either going to get 2 or less, or we're going to get 3. So again, just like all of the individual outcomes combined for certainty, the same thing here. This 2 or less would include everyone but 3. So if we included that in the complement, we do have 100% of the outcomes again. Okay. So again, here's our graph. If we were to graph something like this, okay, this is showing the probability that the number of heads would be less than or equal to 2. So it includes the 2 block. This is 2. It includes the 1. It includes the 0. So if we're looking at that, it's easy to see that that probability is definitely in our favor, right? There's more. It's more than likely in this case, or it is likely that this is going to occur. Okay. So let's look at another example. What about the probability that the number of heads from a 3-coin flip is less than 2? What would that include here? It couldn't include 2 because it doesn't say equal to. So it includes 0 and 1, which is a combination of 1/8 plus 3/8, 4/8, or 1/2, 0.5. Okay. Again, there's my graph. Okay. The shaded in pink area here represents the probability of 0 or 1 as an outcome. It excludes 2 and 3 as an outcome. Okay. So let's think about a different random variable. We've been thinking about x as being the number of heads in a 3-coin flip. Let's go to a different one. Let's say we roll a 6-sided die. If you roll a 6, you win $10. If not, you lose $1. Talked about this example earlier. How about y is going to represent how much I'm going to win in one play? Okay, so what am I going to do in a play? I'm going to walk up, I'm going to roll the die. If it lands on the 6, I win $10. If not, I lose $1. Okay, so let's think about that. In terms of the outcome for y, what are the possible values of y? Remember what y represents, how much I win. So y can only be represented by 10, which is because it's possible for me to win $10, or a -1, because that would be in the scenario I lose, I would have to pay $1. Okay. Now, how is this probability determined? Why 5, 6 for the -1? Why 1, 6 for the 10? Because we know a die has 6 sides, and rolling a 6, which would give me the 10, is only one of the possible 6 outcomes. Rolling a negative anything else would make me lose $1. And since those other 5 out of 6 outcomes would you end up with me losing, that's why we have that as the probability there. So again, if you're struggling with reading these, start by putting it into context. The probability of the amount that I win being equal to -1, or losing $1, is 5/6. The probability that the amount that I win is equal to $10, which would equal winning, is 1/6. Okay. So now when we do these kinds of distributions, over time, we can start using these distributions to think about what we would expect to happen. A lot of times, that is one of the major applications for probability studies. We want to know, what do we expect to happen? If we know what's most likely to happen, then that can help us make better decisions about our choices that might influence a great many things. Okay, so expected value, that's sort of where we get into considering the idea of what value for the random variable that you're finding the probability of. What do you expect to happen? What is the most likely result in any of these given circumstances? And we talked a little bit about that. Okay. If you remember back when we looked over here at the coin flips, what did we say we expected to happen? We expect to get a 1 or a 2 because we see the probability most highest there. Okay. What about the game where we roll a die? We expect to mostly have to lose $1, okay, because that probability is higher. So, in common sense ideas, we can kind of get an idea of what expected value is, but it does get a little bit more detailed. So, let's look at that. Okay. If I get to expected value, oh, am I going too far? Yes, I did. I get to expected value. Again, like we said, it's what to expect on average. Suppose that you play the dice game many, 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 many times. On each play, you either get $10 or -1. About how much would you expect to win per game on average? This is called the expected value of Y, or you'll see it notated EVY for short. Okay. Now there's a formula for calculating this. Now this looks like a big scary formula, but it's not. Mostly what freaks people out here is it uses the summation symbol. Okay. Basically, what this means is that we take the value itself, the possible result of X, multiply it times the probability of it happening, and we add all those up for each of the possible outcomes. That's what the summation symbol represents, adding them all up. Okay, so let's look at some examples. Here's our coin flip game. Okay, so we have -1 here, which we expect to happen most of the time. We expect to have, because there's 5/6 of the time we're going to lose $1. Okay, so we took the outcome itself and multiplied it by the probability. Okay, we also took the other outcome of $10 and multiplied it by the probability of it occurring, which is 1/6. So if I'm looking only at a single event, I expect that single event to be a loss because there's a greater probability of that. However, what the expected value takes into account is if we were to do this an infinite number of times. Now, what would we expect? Approximately 1 out of every 6 times we'd win $10. So even if we lost $5 on the other 5 outcomes, we would still be ahead 5, right? So that's why when we calculate this, we don't get a negative number. We don't get an expected value of a loss. We get an expected gain of about 0.83 or about 83 cents if we're thinking about money in this case. Okay. If I'm looking at one single flip, if I'm only going to play one time, then I expect to lose $1. However, if I'm going to play over and over and over an infinite number of times, then overall, I expect to come out a little bit to the positive just because this is so much, the win is so much higher than the loss. And we expect to be able to win on average about 1 out of every 6 times. Okay. Even if I lose the other 5, then I still am $5 to the good. So over time, this would work out to be approximately about a 0.83 as an expected value. Okay, so it makes sense. Play the game many, many, many times. You expect -1, you expect 10, just as we described. Okay, so recall flipping the coin. This is the same distribution, that probability distribution we saw earlier. If we flip the coin 3 times, we're counting the number of heads. We have a 1/8 probability of getting 0 and 3, but 3/8 each of getting 1 or 2. So if we look at this as a single event, a single point where we flip 3 coins, we probably expect it to be between 1 and 2. Okay. Over time, that's probably going to hold pretty steady here because we see a more even distribution in terms of the probable outcomes. Okay, so let's look at this. How would RStudio do it? You can put this into R by making a list of your random variables. In this case, it was 0, 1, 2, 3. And anytime we're making a list in R, you'll see us use that little C. You also can store a list of the probabilities of each of those outcomes. 0 was 1/8, 1 was 3/8, 2 was 3/8, 3 was 1/8. Okay. Then the expected value is just the sum of the products of the two lists. And R knows how to do that, multiplying matching elements here. Okay. So if you did the sum of these two lists times each other, R could produce that result for you if you wanted to use R. Again, I am usually not very enthusiastic about students storing tons and tons of lists in R. You can always do that if it floats your boat. But we're just not in a class where we're going to come back and reuse those lists very often. So it's kind of a lot of effort for a one-time use. If it were me, I would probably attempt to calculate this by hand if it wasn't a very large probability distribution. Okay, so how do we do that? We use that formula that we saw over here. Okay, the sum of all of the results times their probability. That's exactly what this formula says. So if I look at this, this is the sum. We see all of these being added up of the result 0, 1, 2, and 3 times their individual probabilities. So 0 times 1/8, 0. 1 times 3/8, 3/8. 2 times 6, 3/8, 6/8. And 3 times 1/8, 3/8. When we combine those all together, 12/8 or 1.5. As long as it's not a really large probability distribution, I'm most likely to calculate it by hand rather than create lists in R, although either option exists for you. Okay, so now once we've got an expected value, that's kind of like the middle. So if we were to do this like an infinite number of times, we would see the most frequent result kind of in that middle 1 to 2 heads if we use the coin example. So just like before, when we thought about mean being the middle, we also need to know, just for a random variable here, even though we know what's the middle and the expected value, we also want to know how much that spreads out, like how much variability there is in that. So standard deviation would be something that we would have to calculate here. Okay, we call it standard deviation, just like we call standard deviation of a particular set of data points. However, the calculation, you'll notice, looks a little bit different. Now, again, this looks like a very mathy formula. However, if we stop and think about it, it's really not that bad. We've got the square root of the sum of any of the expected or any of the possible values for a random variable minus the expected value squared. So this is just like when we took the original data points and we subtracted the mean. Remember, we did that to calculate standard deviation. That's exactly what's happening here. We take the possible result and we subtract the expected value, and then we square the difference. We're finding the deviation and we're squaring it. That's exactly what we did when we were calculating standard deviation with a set of data points. Then we're going to multiply that by its probability of that particular result. Okay. Once we do all of that, we're going to add them up. That's what this summation is for, and then take the square root. Okay. So here's a worked out kind of example of that. So we saw the possibility of 1, 2, 3 heads in the coin example. We calculated the expected value already to be negative 1.5, or I'm sorry, 1.5. So if we subtract it from each one of these results, these are the deviations that we would get. Okay. Again, remember, we know deviation, standard deviation is a distance. We don't want to include negatives. So if we square those, we've eliminated the negatives. And then we have the individual probabilities of those results. So we're going to take this probability times the deviation, and we're going to add those up. That's what you see happening down here. The deviation squared times the probability. The deviation squared times the probability. Same thing, and we have them all added up. Once we do that, square root, boom. Okay, so what does that help us know? Anytime you flip a fair coin 3 times, the number of heads will differ. Okay, we expect it to be about 1.5. Now we know that we're either going to get 1 or 2, but again, statistically speaking, 1.5, but with a standard deviation of about 0.8. So if we subtracted that and added it to the expected value, just like we did with mean and standard deviation last week, we expect, about 2/3 of the time to get between 0.6 and 2.3. Okay. Now we know this is a discrete calculation, it's not continuous. So we're probably going to expect somewhere between 1 and 2, which is what we already knew. Okay. So typically you're supposed to get 1 or 2 heads. Note that getting one of those outcomes should occur 3/4 of the time, not too far off from the 2/3 figure we discussed earlier. Okay. So what would we think? What is the standard deviation of y, our winnings in the dice game? Okay, we're going to try to give that a try. That's one of the things we're going to talk about in class. We're also going to be working on a different random variable probability distribution to see if we are able to work through this and calculate this on our own.